Hello everyone, welcome you all to the live session 12 on the course of fundamentals of manufacturing processes. Here we will be solving some of the sample problems based on the video lectures of week 12. So let's quickly get started with the first question. Please read the question. First of all, you can try by yourself. After that, I will explain you the solution of this question. Hello. Hello, Narottam sir. Do you please read the problem and try to give the answer in the chat box? Yes, correct. So now I will explain why the martensitic transformation during the heat treatment of steel it is a diffusion-less transformation, uh, and how it does happens. So uh, if you can recall uh, the CCT diagram of steel, then how it look like something like this. Here we have temperature, here we have time, and initially we have austenitic steel gamma, and this is the line for perlite uh, perlite formation beginning. Basically here it's the beginning of start of the perlite formation. Similarly, this is the end of perlite formation. And likewise here this line is for the martensitic transformation to begin, MS, and MF is to finishing of martensitic transformation. So what we have initially, we are with the gamma phase, and now in the heat treatment step we know we first austenite the steel. After that we cool it down, and depending on the different cooling rate we get different phases and different properties in the steel. So let's talk about if cooling rate is very slow, what will happen? Like this. So here the cooling rate is very slow, then we will get a coarse perlite. Slow cooling and this is called annealing. So what we get in the perlite. So basically, if we slow down the cooling rate, what will happen? Our austenitic steel will transform into alpha plus cementite Fe3C. This is called perlite. And we know what is the crystal structure of austenitic steel. This is the crystal structure of austenitic steel is face center cubic. And when this austenitic steel or gamma transform into alpha plus Fe3C, then what structure we will get? That we get alpha, we get BCC, and Fe3C, it becomes orthorhombic. And this transformation happens at very slow cooling rate. Slow cooling rate. Since the cooling rate is slow, the austenitic gamma, this gets sufficient time for diffusion. But suppose if it won't get sufficient time for diffusion process to happen, then what will happen? So if the cooling rate is very very high, then our transformation curve will look like something like this. So basically we will bypass the nose of the CCT curve, and our gamma will start to become martensite directly. Here the martensite transformation will start taking place, and further as time passes, the whole gamma will convert it into the martensite. And this is faster cooling. Faster cooling. Faster cooling means the material won't get sufficient time in order to diffusion to happen. That is diffusionless process. Diffusionless process. What's the difference between diffusionless and process with diffusion? So we can understand like this. Suppose we have some crystal structure like this. Some atoms are present on the faces. So if suppose we have one atom and this atom has to go to another place, so if it will go via diffusion, then what will happen? It will go and it will jump to the next place. It will travel complete distance between the two atoms. So that will be a diffusion process. That will be a process which will happen by diffusion. But suppose if this atom does not travels a complete distance of one atomic distance, suppose if it jumps somewhere in between, then that is the diffusionless process. And if jumps to the one atomic distance, then that is called process with diffusion. So if material won't get sufficient time, then diffusion will not take place, and in that case the atoms will get very small time to move, and therefore they will not able to jump to the whole lattice distance. So ultimately what we will get, a supersaturated solid solution. Basically we will have initially gamma, and cooling rate is very fast. Insufficient time for diffusion, and it will be converted into the martensite. Its lattice structure is body center tetragonal BCT. It is a we can say it is a distorted form of body center cubic. So because of insufficient diffusion or diffusionless process, we will get solid solution of iron and carbon, and that have the crystal structure of body central tetragonal, and that is called the martensite. It is very hard and brittle. So in the heat treatment of steel, if the cooling rate is very faster, then the material will get insufficient time for diffusion, and in that case martensite formation will takes place. So the correct answer for this question is, in heat treatment of steel, martensite formation is a diffusionless transformation. If diffusion will happen, then we will not able to get martensite. We will get either coarse perlite, otherwise we will get fine perlite. So we will get perlite or benite. But if diffusion will not able to take place, then we will get martensite. What is martensite? It's a supersaturated solid solution. Okay, so the correct answer for this question is the first, diffusionless transformation. So it is clear to everyone, or if anyone of you have doubt, please ask me, otherwise we will move to the next question. Okay, it seems there is no doubt. Let's move to the next question. Please read the problem and please try to find out the correct answer. Meanwhile, I will create the polls. You can keep your response in the polling section. I will after that I will discuss the solution of this problem. Yes, polls are live. You can give your response in the polling section. I have received one response. I am waiting for others. Okay, I think Yeah, I think others are struggling to understand the problem, so let's discuss it together. So, in the question, in the heat treatment of steels, improvement in ductility and toughness is obtained through, and these are the some of the names of the different types of heat treatment process of steel. First one is hardening. Second is nitriding. Third one is tempering. Fourth one is normalizing. So again, let's try to see. Uh, Again, we will have CCT curve similar to previous one. It is ms, it is mf, temperature, time, and initially we have austenitic. Basically, we uh, we bring we bring the steel to the austenitic state, and later on we try to cool it down, and during the cooling, we by controlling the different cooling rate, we try to improve the property of the steel. So in this question it has been asked, in the heat treatment of steel, improvement in ductility and toughness. So here the desirable properties are ductility and toughness. So initially we have austenitic steel, and suppose if the cooling rate is too high, then what we will get? We will get martensite, and we know martensite is very hard and brittle. So it will have very less ductility, as well as it is not tougher. And suppose it is for faster cooling. If the cooling rate is very slow, what will happen? Very slow cooling, then we will get a coarse perlite, and we know what is the properties of coarse perlite. It is very ductile, but its toughness will poor, so it will not that much tough. Toughness is, it has low toughness, but in the question it has been asked, we want ductility as well as toughness. So how to achieve that? So if you can remember one of the process which has been taught in the video lectures, that is called tempering. What we will do in the tempering? Okay, let me remove some of the things. Okay, here again we have similar kind of continuous cooling curve. Here we have austenized phase, and what we do, we just start our cooling at very faster rate, but we will not bring the material to the room temperature. We will stop just above the martensite formation temperature. So here we have ms, and if we hold, if we control the temperature in such a way so that our cooling will stop just above the martensite formation temperature, like here. So initially we have austenite and cooling is very fast, and we hold the temperature just above the bottom side formation temperature. And then what we'll do, we hold the material at the same temperature, and as time passes, what will happen, the material will start getting transformed to a new structure that is called bainite. And bainite have very good property. After the transformation into bainite, we can further cool it down, so we will get here bainite at the room temperature. Bainite at room temperature. And this bainite have a good balance of ductility as well as the toughness. So it will have good ductility and toughness. Whereas if we would have cooled it down to room temperature at very faster rate, then what would have happened, we would have got the martensite that was very brittle and hard. If the cooling rate was very slow, then we would have got the perlite, coarse perlite, and that is very ductile. So therefore there is a voice way of getting a very tough and ductile form of steel, that is called bainite form, and that we get from the process called Aus tempering, and the process already we have discussed. So correct answer for this is the Aus tempering. By the Aus tempering we will get, if we do the Aus tempering of steel, then we would get good ductility as well as the good toughness. So correct answer is Aus tempering. So I have explained the answer. If any of you have doubt, please ask me. Otherwise we will move to the next question. Okay.
Hello.
Yes.
Good evening, sir.
Yeah, good evening.
Sir, actually, I don't have any doubt in this question. Actually, I want to point out one doubt in assignment number 9, sir. Can I tell you, sir?
Assignment number 9. Basically,
actually, sir.
Okay. Yes.
Actually, sir, just I want to point out one thing, sir.
Okay.
Actually, sir, in assignment number 9, question number 8, there is a numerical.
Okay.
And in that numerical, the question asked about specific grinding energy, sir.
Okay.
So, sir, actually, I have found out the answer as 2.45 joule per mm cube.
Yes.
But
there
in that question,
correct. You are correct. There was an error in that question.
Yes, sir.
So basically, none of the answer was matching. Okay.
Actually, right, sir. But in solution,
Okay.
but in answer 1.65 was given. But in the solution provided by you people, sir, the solution is 2.47. That means it is near to 2.45, sir.
Yeah. That is very close to your answer. That can be because of the precision of the calculator you used and we used. So that can
Right,
be the
sir.
reason. Otherwise, you are correct. Your approach is correct. So
So, sir, the marks will be, sir, awarded in this question or not?
yeah. You will get marks.
Okay.
Your answer is very close to our solution. So you
Right,
don't
sir.
worry.
Right, sir.
You will get.
Right, sir.
Yeah.
Right, sir. So that was my point, sir. So that please, matlab make this point into your notice, sir.
Sure.
Okay. Right.
Okay.
Right. Thank you,
Yeah.
sir.
Yeah. And if there is any doubt in the approach of that solution, or it is clear to you,
Sir, it is clear to you.
Okay.
Actually, sir, similar question was asked in GATE examination also once.
Okay.
So there is no doubt, sir.
Okay. That's fine.
Okay.
Okay.
Thank you, sir. Thank
Okay,
you. Sir.
welcome. Okay, shall we move to the next problem?
Yes, sir.
Okay, thank you. Please read the problem and try to give the answer in the polling section. Meanwhile, I will create the polls. After that, I will discuss it together.
Sir, I am unable to give the answer by polling. Sir, how can I poll, sir?
Okay, if you can see uh, in your device whether you are using laptop or phone.
Sir, I am using mobile phone.
Okay, there you will find activities section. Basically, that
Right, right, sir.
yeah. If you open the activities, you will find the poll.
Okay, okay, right, sir.
Okay.
Sure, sure.
Okay. Okay. Now you can able to give the answer in the polling section.
Right,
Okay.
sir.
Yes. Polls for question 3 is live. You can give your response in the polling section. Till now, I have received only one response. I am waiting for others. If there is any confusion in the question, you can ask me. Okay, I have received a couple of responses, and one of you have got the correct answer. So let's discuss it together. So in this send.
Sir, I'm not able to actually click this response. It is not accepting.
Okay.
Actually, I have like clicked point 3, but
Surface layer deformation, right?
yes, but it is, yes, it is just processing, not showing that it is done or not.
Uh, okay,
I
I
clicked
can.
I clicked point 3, then I clicked vote.
Yes, yes, that is the your process is correct. So that
Then it is
uh,
not done, sir.
yeah, I have. Okay, it is showing. Still, it is showing processing.
Yes, sir. I don't know what is happening.
Okay, it may
It's
be because of some internet
okay,
issue
sir.
or something. But
Right,
anyway, your answer is correct.
right, sir. Right, sir.
Okay,
Thank you, sir.
yeah. So here the sandblasting in the question it has been asked the sandblasting. Sorry. Yes. Sandblasting process of surface modification is based on. So uh, we have learned many kind of processes where we want to improve the surface property of our component, and one of the process that we have learned that is called the sandblasting. What we do in the sandblasting, or let's say something uh, it grade blasting is also used, or shot pinning, so all are similar kind of processes. So uh, what we do, suppose we have a component like this, and this component this component suppose it is very soft, as well as some if on the surface properties, if we'll see, it will have some tensile residual stress. So but for our application, what we need a material which is which don't have tensile residual stress on the surface, or we want hard surface, so that our wear so that the wear of the component will become slower. So in that case, what we have to do, we have to improve the hardness hardness or strength of the component. And one of the processes we know is by the surface modification by work hardening or surface layer deformation. So if you have attended my previous lectures, there we have discussed about the work hardening. Work hardening means improvement in strength or the hardness of the material because of the plastic deformation. So what we do, we take lots of sand particles or grit particles and we give them high velocity. So high velocity sand particles or grits, they are bombarded on the surface of the component, whose surface property needs to be improved. When these particles comes and strikes to the surface of the material, then what happens? The zoom version is shown here. So here we are focusing just on the one sand particle or the grit. So high velocity or high kinetic energy high velocity ball comes, and because of impact it deforms the material locally and plastically, and this deformation is permanent deformation. And we know if some material or metal deforms plastically, then what happens to its strength? Its strength increases or material become hardened. That is called work hardening or strain hardening. As well as what else happens? So if we again zoom it out and if we try to see, so because of the impact of the sand grit, there is a plastic deformation which is like this, and near about this a very locally if we see, the compressive stress gets generated, and this because of this compression stress or compressive residual stress, the surface property is improved. Which properties? Basic, that is fatigue property. Basically fatigue life of the component, it gets improved. We know if component have tensile residual stress, then it has tendency for distortion. Why? Because during the cyclic loading the cracks gets nucleated on the surface, and if it has tensile residual stress, then it is very easier for cracks to move forward and component gets failed. In order to avoid that situation, what we do, we impart or we induce compressive residual stress, and we know compressive residual stress helps to reduce the tendency of distortion or crack formation or crack nucleation. Therefore there are two advantages because of this sandblasting. The fatigue life is improved and wear resistance also improved. So, and that happens because of a thin layer of surface gets plastically deformed, and finally what we will get? Compressive residual stress. So correct answer for the sandblasting process is the surface layer deformation. So I have explained the solution. Still, if any of you have doubt, please ask me. Anywhere, any step, if it's not clear, please ask me. Okay, it seems it's clear to everyone. So let's quickly move to the next problem. Even later on, if you find any difficulty, you can stop me and ask. So as of now, I am moving forward. Please read the question, and you can give your response in the polling section. Meanwhile, I will create the polls. Yes, polls are live. You can give your response in the polling section. I have received one response. I am waiting for others. Okay, yeah, I have whoever have answered, they are correct. So the correct answer is uh, compressive residual stress. And let's quickly see what is the burnishing process, and we will try to see uh, a little closer look on the burnishing process. So if you if I want to tell you what is the definition of the burning process, it is the uh, basically plastic deformation of uh, the workpiece by the uh, relative movement of tools, and that plastic deformation is very local deformation, as we have seen in the earlier process, sandblasting process, where the high velocity sands were coming and they were creating plastic deformation in very localized region. So here also the plastic deformation is happening, but not it is happening up to the very small depth. And here we can see, here we have a shaft, and this is the burnishing tool. And what this burnishing tool is doing, it is just deforming the shaft on the surface. And so what will happen, basically whatever the asperities will remain on the shaft surface, they will get uh, they will get plastically deformed, and surface properties will get improved. Surface roughness also gets improved, as well as the surface will become hardened, so it will improve the fatigue life. So just if you zoom it out and we'll try to see here. So let's suppose this is the initial workpiece, or let's say shaft we have, and if you closely look the surface, then there are this kind of irregularities will be there. And because of this, first of all, its surface roughness will be poor, as well as there are its fatigue life will be poor, because uh, there are chances that on the top surface it will have tensile residual stresses. But if we do burnishing process, in burnishing process what we do, this is our burnishing tool. Burnishing tool and we are deforming the shaft or the workpiece with the help of our burnishing tool. What is doing, it's just rotating over the workpiece, and same time we are applying some normal force, and this is burnishing tool, its hardness is higher than the workpiece. Therefore, when it comes in the contact of the workpiece, by due to the application of this normal load, this expertise or this uh, local deformation, this local expertise gets deformed, and here we get good surface finish, as well as we get compressive residual stress in this zone. Earlier, there are high chances that the material have tensile residual on the surface, but because of the burnishing we were able to improve the surface finish, as well as we will able to induce the compressive residual stress, which increases its aesthetic wise also, as well as its fatigue life. So the correct answer for this problem is the compressive residual stress, and these expertise are plastically deformed. Okay, so correct answer is the compressive residual stress. So the I have explained the solution of this problem. So still, if any of you have doubt, please ask me. Anywhere, if there is any issue anywhere in the
No, sir.
expression. Okay, let's move to the next problem. Okay, please read the problem and try to find out the correct answer, and you can give your response in the polling section. Yes, polls are live. I have received a couple of responses, and I am waiting for others. Okay, I have got the mixed response, but one of you have got the, I think, sorry, none of you have got the correct answer. So let's discuss it together. What happens in the ion implantation technique? So it is also a method of improvement of surface properties of the material. So how it is done, or how it is look like. So the initially what we have, suppose we have a material, substrate material, like this. This is our substrate material. And here basically this is the technique. Ion implantation method is a method to improve the surface properties by changing the chemical composition. Most of the time the chemical composition of the uh, surface of the material gets changed. So what we are doing, we are trying to deposit, or we are trying to mix the material which are near to the surface with some other materials, so that the properties of substrate material gets improved. So how it is done? By the ion implantation technique. So here suppose we have some material uh, which we want this material should get, and it should go and deposit on the surface, as well as it should go inside the near surface material of the substrate material, so that properties of substrate material gets improved. So how it is then? So first of all, the material which is which needs to be deposited, that uh, we we bring into the gaseous form, or we try to uh, convert the material into its atomic form. And same time, what we try to do, we try to increase the velocity of these materials, so that when this material will go, it will strike on the surface of the substrate material, and it will able to go inside the substrate material, and it will go and sit wherever it find the space. Either it will go substitute the substrate material depending on the size, or it will go and go sit into the vacancies. So, and there is some ion beam, and what what they are doing basically, if if we have ions, then what we can do, we can increase its velocity by applying electric and magnetic fields. So we can control its velocity, and our target is to improve the velocity of these materials. So suppose these materials gets vaporized, they are here and there, but they will not automatically enter into the substrate material. For that, these ions come they collide with them, and when they collide, they transfer their kinetic energy to these atoms, which needs to be deposited. And then they will go and they will form bond between the substrate material, and they will go inside the material near the surface. And this is process is called the ion implantation technique. And when these materials go and hit the material which are near the surface, suppose earlier our substrate material was like this, so it is in the crystalline form, it has a regular atomic arrangement, crystalline form. So basically the atoms are arranged. When these high velocity particles and ions came, they hit it, this what will happen, they will shift from their position, they will go somewhere here. Similarly, some this atom came and it collides here, it will shift to here. So likewise, the surface atom, few layers of the surface atom of substrate material gets distorted. Earlier they were in very good crystalline form, but later on what happens, like this, some will go there, so they will become a kind of amorphous, so their crystallinity go away because of collision of ions, as well as this material which needs to be deposited with the substrate material. So little bit loss of crystallinity will be there. Loss of crystallinity will be there. And because of the loss in crystal structure, the correct answer will be the third one, damaging crystal structure. and wherever the crystal structure will lose, the other materials will come and they sit like here, 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 here. They will come and sit, and we get improved surface properties. This technique is also used in some semiconductor industries for doping purpose. So it is uh, it is widely used in semiconductor industries. So correct answer is the damaging crystalline structure. Whereas in other processes, the crystal structure of substrate material is not changed at all. So I have explained the solution. Still, if any of you have any doubt, please feel free to ask me. And if it's clear, so let's quickly
Yes.
move to the next problem. Okay. Please read the question and try to give the find out the correct answer. You can give your response in the polling section. Polls are live. You can give your response in the polling section. Yes, I have received a couple of responses and both of you are correct. So for others, I will quickly discuss the correct answer for this problem, and I will tell the solution. So the question is all about the diffusion of carbon in carburizing process. We know the carburizing process is the one of the process of improvement of surface property. Especially by the carburizing process, we try to improve the hardness of the materials. So wherever we need wear resistant properties, what we do, we uh, go for the carburizing process. So what, suppose we have some component like this, our substrate material. Substrate material, or we have some ferrous material, which is suppose we have a ferrous alloy whose uh, which is not so hard, or it is too much of too ductile, and one of the and we know, for especially for the ferrous material, if we increase the carbon content, then the its hardness improves, or hardness of ferrous material increases by increasing the percentage of carbon to a certain limit. So for that, uh, what we do, we try to, if this material, substrate material, is not very hard, then what will happen when it will come to the contact, suppose we have gears. This component is, let's say this is gears. It is not very good looking gear, but still you can understand. So basically we have two gears, and they are in the mesh, which is there. So likewise, since here if we see, they are coming into the contact, and if they are softer, at least on the surface, then what will happen, then they will, the teeth will wear out very quickly, and very soon the functionality of gear will be lost, or there will be some free play. uh, their teeth will not mesh correctly, and because of that uh, there will be loss in accuracy of the component. So in order to avoid this, what uh, what is done, the surface properties of the gears is improved by the improving the hardness by the carburizing process, or sometimes nitrating process also used, improving hardness. And if you improve the hardness, then wear process will become slower and component life will become larger. And for that, what we do, we bring this gear in carbon rich environment. It is the carbon rich environment. So basically this is our gear, and here we have, this is the carbon rich environment, or the compounds which have carbon. They can be either in the gaseous form, or they can be in the solid form, or in the liquid form. But the surrounding, this substrate material is surrounded by the carbon rich materials. Then our aim is to improve the surface hardness of the substrate material, and that can be only possible by if the carbon material will go and they enter inside the substrate material. And how this is done, if this thing, if all this setup will kept at the room temperature, then nothing will happen. Basically these atoms, very few atoms will come and strike to the material, and further they will not go inside the substrate material. For that we have to increase the temperature, and we know there the process which is called the diffusion, which happens because of the concentration gradient. So we know in the in nearby region we are providing high concentration of carbon. High concentration of carbon, or carbon rich atmosphere. Because of this high concentration outside, and inside we have low concentration of carbon, then because of diffusion, the diffusion process will take place because of concentration gradient. And what is diffusion process? The atoms from high concentration region go to the low concentration region at some elevated temperature. So there is a minimum temperature which is required for diffusion to happen, and after that temperature, if you further increase the temperature, then our diffusion process will become faster. So what happens, first we created concentration gradient. First thing is concentration gradient is generated. Concentration gradient is generated by putting the substrate material in carbon rich atmosphere. After that, second step, the temperature we increased. So temperature we increase so that diffusion process should get start, so that atoms from high concentration region able to move to the substrate material or the surface of the substrate material. So temperature we increased. If temperature is higher, then the process will become faster. Why the process will become faster? High temperature means the atoms are moving faster. If atoms are moving faster, the more number of atom will come on the substrate per unit time. So high temperature means more number of atoms are striking to the substrate material per unit time. Therefore, the diffusion will become faster. And third thing is the time. So we expose the substrate material in the carbon rich environment at high temperature for if we expose it for shorter period of time, then the depth up to which carbon atoms will enter, it will be less. But if we give sufficient time or more time, then the depth up to which carbon diffusion will happen, it will be higher. So these three things are responsible for diffusion. And if we increase any of these, temperature, time or concentration gradient, our more number of carbon will get diffused to the substrate material, and this process is called converging process. Similarly, sometimes nitrogen is also introduced into the substrate material to improve the surface property, that is called nitriding, but the mechanism is same, diffusion. So if we see, the correct answer are all of these. Temperature higher, higher diffusion rate. If time is higher, if time is longer, then more number of carbon atoms will diffuse to the substrate, and the diffusion the depth of the diffused carbon layer will be higher. And if carbon enriched medium, if the concentration of carbon is high, then also the diffusion rate will be the faster. So correct answer is fourth one. So I have explained the answer of this question. If any of you have doubt, please ask me. Otherwise we will move to the next problem. Okay, seems there is no doubt. Shall we move to the next question?
Yes, sir.
Okay, please read the problem and try to give the answer in the polling section. Polls are live. Please give you can give your response there. Okay, I have got a couple of response. I am waiting for others. Okay, yeah, most of you have got the correct answer. Okay, let's quickly discuss it together. I will try to explain the reason why it happens. Otherwise, all of you already have got the correct answer. So the correct answer for this is the basically, first I will read the question. In hot tipping method, chromium improves, and these are the property: fatigue like of component, toughness of material, corrosion resistance of material, and last one is the all of above. So the correct answer is the corrosion resistance of the material. To understand why it happens, let's quickly look at the Ellingham diagram. If you can recall, what is the Elegam diagram? Basically, here on the we have on the y-axis it is shown the Gibbs free energy, or delta G. It is the Gibbs free energy. And on the x-axis it is temperature. And what what is shown in the plot, basically here it is the oxidation tendency, or there is reaction with oxygen for different material is listed down here, and for different temperatures. And we are trying to see what is the Gibbs free energy of the reaction, or what is the Gibbs free energy of the during the oxidation of that component. And if you remember the thermodynamics, then if the delta G, or Gibbs free energy of a reaction, is negative, then it is most likely to happen that reaction. So if Gibbs free energy will be more negative, then reaction is happens that reaction is spontaneous, and that happens very quickly. So here, for different materials, if we try to look, here we have copper, and here ferrous material like these two, and zinc, manganese, and here we have this one. This is for the chromium. If you see the chromium line, this is the chromium line, and I will hash the iron line also somewhere here. That is the line for the iron. There are two lines, basically two types of reaction happens with the oxygen for the iron, so we have two lines. But both of these reaction of oxygen with the iron, those lines are coming above the reaction of chromium with the oxygen. So chromium line is coming at the below of the iron line. What it means? It means for chromium, at any temperature, if we see, the Gibbs free energy for the chromium to oxidize, it will be more negative in comparison to the oxidation of iron. Or we can say the corrosion of chromium. What is corrosion? Corrosion is the basically formation of oxide. So if we have, suppose if we have iron component like this is Fe. So if someone says it has been corroded, what it means? It means formation of ferrous oxide has been taken place. Fe3O, Fe2O3, or FeO, Fe3O4. So those kind of oxides formation takes place, and this is called corrosion. Now we know the Gibbs free energy for corrosion of chromium is more negative. It means chromium will get oxidized faster than the ferrous material. Then what happens if we coated this material with the chromium? In hot dipping, what we do, suppose this is, here we have molten chromium, we took our ferrous metal and we dipped it inside the molten chromium, and what happens? A layer of chromium, basically this is the chromium layer, that will the iron will surrounded by the chromium layer. And now what will happen? Suppose oxygen comes, it will first come in the contact of the chromium, and it will immediately react and form chromium oxide. So all sides of from all sides, the iron which was surrounded by chromium, when it comes in the contact of the oxygen, quickly the outside the chromium which we have deposited, it will becomes chromium oxide. And the good property of chromium oxide is that it forms a passive layer. Passive layer means once it get oxidized, it won't allow the oxygen to enter the ferrous or iron. So once the chromium oxide forms, it will stop the further oxygen to enter to the chromium oxide, so that the oxygen will not able to reach to the iron component. So it will provide a shield to the iron, so that no oxygen could come and it would not react with the ferrous, and therefore its corrosion properties get improved. So because it happens only because of the properties of chromium oxide, which forms a passive layer, and it further it stops any kind of corrosion. Therefore the correct answer is corrosion resistance of the material is improved by hot dipping method, and by doing the chromium coating. So I think I have explained the solution, but still if any of you have doubt, please ask me, otherwise we will move to the next problem. Okay, it seems it's clear, and now you must have understand what is the reason. So let's move to the last question of the day. Please read the question and try to give your response in the polling section. Yes, polls are live. You can give your response in the polling section. Yes, you can give your response in the polling section for answer 8. And still if any of you have doubt in understanding the question, please ask me.
Hello.
Yes.
Sir, actually, I'm not familiar with this question.
Okay. So I can help you. I can give you a hint. Basically,
Right, sir.
yes. Uh, it is a basically surface building technique. In surface building technique, if you remember, then what we do, we have a substrate material, and we we suppose our surface is not too good. If you want to improve the property of the surface, then we deposit some extra material. Basically, it's in the solid form. We deposit this material, and then what we do, we try to melt both of the material. Substrate, this is the deposited material, and this is the some layer of the some layer of the substrate
Parent
material.
metal.
Yes, parent
Okay.
metal. We try to melt both of them, so that there the the bonding between two metals can happen, and they they will the surface property of the parent metal gets improved. So what we do, there is some thickness of parent material gets melted, that we call d base, db, or base material, depth of the base material which is melted, and we have deposited some layer of our target material, or material which is to be deposited on the base material, that we called ds. And there is a term called dilution, and dilution is defined by the thickness of material which is the thickness of melted base material, or db, divided by db plus ds. So
Right.
this term is called dilution. Now you can try, and probably you can able to find the answer. You can take some time.
Right, sir.
Okay.
So it's first one, 2:3.
Yes, correct.
Right.
Okay. uh, so I will also just quickly try to write down the solution. So this is the formula we have. Dilution is equals to db by db plus ds, and it is given 40%. So if we write, if we try to substitute the values in this equation, then here we can write 40% means 0.4. If we write it in the terms of fraction, equals to db divided by db plus ds, and further solving we'll get 0.4 db plus 0.4 ds is equals to db. On further solving, oh sorry, we will get 0.4 ds is equals to 0.6 dB. And what has been asked in the problem, we have to find out the ratio occurs in the base metal to the depth of surface material, or dB by ds we have to find out. So dB by ds, it will comes out 0.4 by 0.6, or it will be equals to 2 by 3. So the ratio of material which was melted with to the ratio to the material which was deposited, this ratio will come out 2:3. So the correct answer is the first one. So this is the
Yes, sir.
solution. So I think this is clear to everyone, but still any of you have any doubt, please ask me.
No, sir. Thank you, sir.
Okay, so this is the end of this last session of this course. So hope you all you will write your exams well and you will score well and you will get good grades, and wish you all a very happy weekend. Still, if any of you have any doubt, you can reach us from the NPTEL discussion forum. So still, if any of you have doubt, feel free to ask us, and we will try to help you. And if there is
Okay.
still any doubt you have, you can ask me for this session.
Yes, sir. Yes, yes, sir. Abhishek, sir, I just want to ask that, can you tell me about the pattern of question paper which you people are going to ask in the examination? Means how much, what is the percentage of numericals and what is the percentage of theory questions?
Yes, in terms of percentage, it is not. Uh, we, we, we even I don't know, means, because it depends on the professor who is
Right,
instructor, and they are going to set the question. But it will be mixed type. It is we can one cannot define what percentage of numerical will come, what percent of theory will come, what percentage of short
right,
type answer will come, what kind of fill in the blanks will come. It will be mixed.
right.
So pattern, exact number of questions you will come to know only on the day of the examination. But we can tell that you will get multiple types of question. You can get the fill in the blanks, you can get short answer type of questions, and you might have received an email regarding this. I think if you check your email, you might have received and other instructions for the examinations. So if you have gone through the course lectures, you have solved the assignments, and you have seen these live sessions, you're definitely going to score very good, and you are going to get very good grades. So questions will be easier. They are easy to solve. uh, just uh, just prepare well, and study
Right.
thoroughly, and you can revise the every lectures.
Okay.
Okay.
Right, sir.
Yeah,
Right,
question will
sir.
be easier. Don't worry for that. Just study well. Okay.
Yes, sir. Actually, sir, I have already given the power plant engineering examination
Okay.
of NPTEL that was also conducted by IIT Roorkee.
Okay.
So there were 54 questions in four sections,
Okay.
and the fourth section is of 24 questions, sir. So 24 question, all these 24 questions were numerical.
Yes, that can happen to here also.
Okay, right, sir.
So just you feel free from your side. Uh,
Right, right.
just make sure that whatever is going to be asked, it will be totally from the lectures. Out of syllabus,
Right,
you
sir.
won't get any questions. So be free for that, and 110%, 110%, I can guarantee you can solve it within, if
Right,
you
sir.
have gone through the lectures, then you won't face any difficulty. So either it may be numerical, fill in the blanks, multiple choice. So just uh, be open for any kind of pattern, but uh, it might be possible that this time you may get 24 questions from just from the multiple choice or fill in the blanks. Anything can be possible that you can come to know only on the day of the examination.
Right, sir.
So please be open for that, and
Right, right,
prepare
sir.
well. Okay.
Sir, can I know about you a little bit? What you are doing there?
Yes, I am a PhD scholar in the IIT Madras. Uh,
Okay, sir.
yes.
Okay, okay. Okay, it was really a nice session, sir.
Okay, okay. Thank you so much. Thank you so much for your appreciation. And in the next semester, uh, again, I will try to take some course similar to this.
Right, sir.
Okay. Okay.
Thank you so
Still,
much,
if
sir.
any of you have faced any difficulty because of me, I'm sorry for that. Uh,
No, 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 sir. Not at all, sir.
okay, okay. Okay, thank you so much to all of you for
Okay,
Yes.
joining
thank you.
this, and it was nice journey with all of you.
Thank you,
Thanks
sir.
again.
Thank you so much.
Okay, thank you. Bye. Good
Thank
night. Have a good, have a very happy weekend. Bye.
Thank
Same
you,
to you,
sir.
sir.
Thank
Thank you,
you.
sir.
Welcome.